Okay, chapter 21 is on musical sounds. We'll talk about pitch, intensity and loudness, and quality of sounds. So noise is sort of an irregular vibration of the eardrum that's produced by vibrations that have a jumble of amplitudes, frequencies, phases, and all mixed together. So white noise would be an even mixture of all these frequencies. It sort of sounds like shh, and if you plot pressure versus time, you just get this big jumble with no particular frequencies standing out. Music is the art of sound, and musical sounds have a rather periodic and pleasant-looking plot of pressure versus time. And a musical tone has three characteristics: pitch, intensity, and quality. Pitch is related to the frequency of the sound waves, and it's determined actually by the fundamental frequency, the lowest frequency you hear. Intensity determines the loudness of the sounds, or like the amplitude. And quality is determined by the presence of harmonics, or different frequencies all combining to produce the same sound. And these are called partials. And so the relative intensity of all the various partials gives us the quality of the tone. So let's start with pitch. Music is organized into notes. Each note has its own pitch, which we can describe with a frequency. The rapid vibrations, or high frequency, produce sounds with a high pitch, and slow vibrations, low frequency, produce sounds with a low pitch. So in music there's 12 distinct notes. We start with C, then there's, if you go up by semitones, there's C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and lastly B. And if you go a semitone above B, you're back to a C. Each semitone represents a multiplicative step of the 12th root of 2 from the note before it in frequency. And that's about 1.059. And if you multiply 1.059 times itself 12 times, you get 2. And so 2 is the step in frequency from one octave to the next. So this C down here has a frequency of 32.7 hertz. The next C up has a frequency of 65.41 hertz, etc., etc. So different musical notes are obtained by changing the frequency of the vibrating source. High frequency produces a high pitch. Lower frequency, maybe a larger musical instrument, for example, or a more massive one, will vibrate with a lower frequency, and you'll get a lower pitch. And in music, the pitches we use up at the very, very high end, like a piccolo, go up to about 4,000 hertz. That's about as high as you want to hear during music. But in fact, your ear is sensitive up to maybe around 18,000 hertz. Certainly, even some people and most dogs can hear even a little above that. But this upper limit, as we said before, kind of goes down as you get older, meaning that a very, very high-pitched sound above 18,000 hertz might be inaudible to someone like me, but a younger person might be able to clearly hear it. So there was pitch. Next one is intensity. Intensity of sound depends on the amplitude of the pressure variations. So high amplitude is loud, low amplitude is like a whisper. So the human ear responds to intensities from the tiniest little whisper of 10 to the minus 12 watts per square meter. That's called the threshold of hearing. And all the way up to the threshold of pain, which is 1 watts per square meter. That's 10 to the power 12, which is like a trillion times more intense in terms of power going into your ear. Separates the tiniest whisper from the threshold of pain. So because of this big range, the sound scale we use for sound intensity is a logarithmic scale, meaning that as you go up each additive step of 10 decibels, you're actually multiplying times a factor of 10 the actual intensity in watts per meter squared. So we define the threshold of hearing, 10 to the minus 12 watts per meter squared, to be 0 decibels. 10 decibels is 10 times more sound intensity than the threshold of hearing. 20 decibels is 100 times the sound intensity of the threshold of hearing. 30 decibels would be 1,000 times, all the way up to this threshold of pain. It's 120, so it's actually 1 trillion times more intense. This is an air raid siren nearby, and this jet plane 30 meters away is actually 140 decibels. That's above the threshold of pain and can actually damage your eardrums. The sound intensity you can actually measure in watts per meter squared. It's the amount of power per cross-sectional area. But loudness is a physiological sensation. So it turns out that our ear is most sensitive to about 3,500 hertz. It's a very high-pitched note. So a 3,500 hertz sound at 80 decibels sounds twice as loud as 125 hertz sound also at 80 decibels. Okay, so we did pitch, we did intensity. The last one is quality. So we know that if you play the same note on a piano or a clarinet, you can hear the difference. That's called quality or timbre. Timbre describes all the aspects of the musical sound that are other than just pitch or the loudness or the length of the tone. So one way of describing the timbre is to note that a particular tone is often composed of a fundamental frequency and then higher frequencies that are multiples of that fundamental frequency. So this is related back to standing waves, where you can have first harmonic, second harmonic, third harmonic are all integer multiples of frequency. Well, any tone played on a real musical instrument is actually a sum of the lowest harmonic plus a lot of these upper harmonics. So for example, you might get a string that's vibrating both in the fundamental mode and in the third harmonic together, and that will produce a certain timbre of sound. So all these partials, okay, the presence of the partials and the relative intensities of the partials determine the quality of the sound. And so the reason a piano and a clarinet sound different is because they have either different partials or different relative intensities of these partials. And when you add them all up, you get these different shaped wavefronts, or different shaped pressure versus time graphs for piano and a clarinet. So Fourier analysis is the mathematical analysis of these different partials. So Fourier discovered that any wave can be dissembled into a sum of just sine waves. Okay? And so if you have a composite wave, this one down in the bottom, it can be the sum of the fundamental sine wave plus the second and plus the third harmonic. You just adjust the relative amplitudes of these harmonics, and you can make it sum up to look just like this composite wave. So any musical note is actually the sum of a bunch of different sine waves of different frequencies. And that's what we hear. That's how we can hear with our ear and tell different timbres of sound. So an audio recording is simply a way of recording somehow the pressure versus time of a sound. Okay? This is actually the sound of an oboe and a clarinet being played together. Okay? It's some complicated waveform, but a phonograph record actually can record an analog signal which is of this shape, so that when you play it back, that's how it moves the speaker, and that's what we end up hearing. So digital sound is when you take this plot of pressure versus time and turn it into numbers. Each number describes the amplitude at a particular instant of time. And we can record that, all those many, many, many numbers, on the surface of a DVD or a CD. And so this is a microscopic image showing pits, where each little short pit corresponds to a 0, a long pit corresponds to a 1, and many, many of these pits form binary numbers, and each binary number tells you the amplitude of the sound. And then when it gets played back, all that amplitude tells the speaker how to move and how to create that pressure versus time wave, and that's how we hear exactly the music that was originally recorded.